Okay, let's try this. Hello and welcome to week 7 of the online course AC/DC Theory. Good work on your quizzes. Almost everybody did really well on those. Those of you who didn't and don't understand what you didn't do right, give me a shout and I can help you work through that a little bit. I'm going to take kind of last step in what we're doing with our RLC circuits, our resistive, inductive, capacitive circuits. And talk about a thing that we're actually going to see as electricians in the electrical world, and that is the addition of parallel capacitive banks in a system in order to correct power factor. We've been talking about power factor, that is the ratio of watts over volt amps in a system to give us kind of the thing called the power factor, which is related to the angle theta of our triangles that we've been drawing, and also the lead or the lag of the voltage and the current. That power factor is something that is important to electricians because as low as you can get the power factor, as close, I should say, as high as you can get the power factor to 1, to unity, or as low as you can get that angle theta, the less copper you're going to have to put into a system, the smaller your conductor is going to be, because we size our conductors by the volt amps. And as our power factor gets smaller, our volt amps approaches the watts, the true power, which is the thing that's actually doing the work. The book has a really, really good explanation of how to work a power factor equation by adding capacitors in parallel, and you'll find it on pages 599 to 603. And it's got about 5 steps, and none of the steps in themselves are very complicated, but it's nothing that you're ever going to be able to just do unless you do it every day. Just sit down on a piece of paper a year from now and do. But I'm going to show you a method that I think you will be able to do. And it's kind of my cheat method on correcting for power factor. So what I'm not going to worry about is getting exactly to 94 or 96 or 98. Actually, I'm going to show you a really easy way to usually get to 98%. And I'm not going to worry about using a capacitor that is available to me. Because that's a moving target, and you can always get a list of capacitors that are available, and choose something that's close. Someday, if you're a signing supervising electrician and you're working at a big industry installation, you may be asked to do some designing of sizing of a capacitor bank that's put in parallel. In the real world, this would simply be 1 or 2 or more circuits that have capacitors in them in parallel to the rest of your system, which is just another way of saying another circuit in your system. Adding that circuit in parallel is the same thing as changing your total capacitive reactance, the total capacitance in your system as seen by the source or seen by the feeders, which is usually what we're most concerned about. Obviously, if you're adding a capacitor bank, you're going to be adding more copper because you're adding a circuit for the capacitor bank, but it may allow you to size down the circuits for your feeders in the total outcome. It's also something the utility is going to want. We've talked about that before. I want to talk about a couple of concepts that are crucial to this to start off with, and I did for extra credit last week. I asked you guys to tell me, since I didn't give you inductance or capacitance in the circuit, I just gave you the inductive reactance and the capacitive reactance, the X sub L and the X sub C. I asked you as extra credit if you wanted, and a couple people did it, and did it right even, to solve for L and solve for C. So here's the formulas that we know. We know that X sub L equals 2 pi fly. And therefore, if we do the math, remember X sub L is the same as 1 over X sub L, and 2 pi fly is the same as 1 over. So if you do the mathematical gymnastics, what you come up with is L, inductance, equals X sub L over 2 pi F. Now that's handy if you know your X sub L and need to know what your inductance is, and that's a great thing to know. The more important for our purposes is doing the same thing with the formula that is X sub C. So we know right now that X sub C capacitive reactance equals 1 over 2 pi FC. Now if I do the mathematical gymnastics, remember that that's the same as X sub C over 1. Any number over 1 is itself. So by doing that, we can divide this out and do a little bit of again, algebraic gymnastics. And what you come up with is C equals 1 over 2 pi F X sub C. I almost did that wrong right in front of the camera. It's funny how my brain turns off when the camera's on sometimes. But capacitance equals 1 over 2 times pi times F, which in our case as electricians is 60, times the capacitive reactance that you already have. These two are the same formulas, they're just different derivations of themselves. So that's really, really important. And here's the other thing to remember about these formulas, and it's demonstrable in both of them, is that if X sub C goes up and everything else is in a box, then C must go down, or at least some one of these numbers must go down for that to stay a true formula. So same thing here. If capacitance goes up, X sub C is going to go down. If capacitance goes down, X sub C is going to go up. They're invert relations of each other. So that becomes important. So if I need to add more capacitive reactance, often it'll be less capacitance, which is a little bit confusing sometimes. But keep that in mind as we move forward. We're going to be talking about the relationship of current and reactance. Now, as electricians, we use systems that usually are pretty locked in place for voltage. So we're going to be talking about that today. And I'm going to use as an example this circuit that I have on the board, which is a parallel circuit. Now, you can do power factor correction on a series circuit, but it becomes a little bit complicated because if you put a capacitor in series with another capacitor, as we learned earlier, you get less capacitance. So you end up having essentially two capacitors in series which reciprocate. And you get less capacitance, and in a series circuit, you know that in any circuit, less capacitance is going to be more capacitive reactance. But more capacitive reactance, you're going to be possibly making your problem worse. So usually the power factor correction, whether you're working in a series or parallel circuit, you add a capacitor in parallel, or in the real world, we add a bank of capacitors in parallel. So I'm just going to, because when I add a parallel element to a series circuit, we get back into combination circuits that we haven't dealt with since DC, and it gets a little bit more complicated. So I'm going to scratch that right now, and we're just going to look at it from the viewpoint of looking at a parallel circuit. And part of that's because these are online classes. We just don't have as much time. We don't have as much class time to be able to do all of this stuff. So I'm giving you the basics. If you want to know more about it, there's a lot in the series and parallel chapters in our book, in that Delmar's book. It's a terrific book. But for now, I'm going to take this parallel circuit, and we're going to talk about what we've got in this. Now, I've done some of the math to try and keep this short and sweet. I've got a resistor that I've said is 20 ohms. If I've got 100 volts at 20 ohms, I'm going to have 5 amps of current flowing there. If I've got, and I'm going to get a better marker right now also, if I've got a inductor that has got 26.5 millihenries, if I go ahead and do the 2 pi fly formula, that'll come up to 10 ohms. So I've got 10 ohms of inductive reactance, which gives me 10 amps of current flowing through that reactive element that is an inductor. Over here, same thing, I've got 53 microfarads. If I do the 1 over 2 pi FC, I'm going to end up with 50 ohms. If I've got 100 volts, 50 ohms, I'm going to have 2 amps of current flowing that way. So my resultant Pythagorean diagram of vectors, which is 90 degrees like this, it's essentially 290 degrees, is going to look something like this, and I'm going to have 5 amps. Now remember, we're in parallel, so we're working with current, right? And once we've solved current, all we have to do is multiply it by 100 for the volts, and we're going to get power. So the current triangle, or vectors, are proportional to the vectors we're going to get from our power. And now I know we learned power factor equals watts over VA, or true power over apparent power, but it also equals, when we're thinking about the current triangle, it also equals, let's see, I at the resistor over I total. So my current as seen by the resistor over the total current. These are equal and proportional things, and we'll get back to that later if that doesn't make sense. So in this triangle, or this vector diagram that I'm going to make into some triangles, I've got 5 amps in the resistive direction. In my inductive direction, which I like to do upward, I think I did it the opposite way one time, I'm going to have 10 amps of current. And in my capacitive direction, 180 degrees from that, I'm going to have 2 amps. So my resultant triangle is 5 amps and 8 amps. And that's the one I'm going to solve the hypotenuse for. Again, this hypotenuse is going to solve that actual vector that goes in that direction. And I did that by subtracting 2 from 10. Now, a couple of you forgot to do this step in a couple of your triangles earlier, and it cost you some answers. So remember, this and this is the first thing I have to solve. I have to take away the two things that are 180 degrees from each other. I have to take the smaller from the larger. It doesn't matter which is which. However, you're going to find that almost all circuits are inductive. They're not capacitive. Capacitance is something that usually is a result of a little bit of capacitance for like motor starters and things, and just unavoidable capacitance on the line. Capacitance isn't something that we have a lot of naturally in a circuit like we do inductance. I mean, almost everything is an inductor. A transformer is an inductor, a ballast is an inductor, a motor is an inductor, a solenoid is an inductor. Any actuator is an inductor if it's electrically operated. Back to this triangle. So what I've got is I've got 5 amps, 8 amps, and my resultant, if I do my Pythagorean, I'm going to square 8, and I'm going to add it to the square of 5, and I'm going to take that square root, and I've already done the math at home, so you don't have to watch me punch in a calculator. I get 9.43 amps. So again, this triangle is proportional to my power triangle. If I just multiply each one of these numbers by 100, I'll get my other, because I have 100 volts and voltage is the same everywhere in a parallel circuit. You guys already know that. So I would essentially have 800 VARs and 500 watts and 943 VA. That would be the same triangle. So rather than going into that, I'm just going to stick with this current triangle for now, because this is a current variant. There is a current divider going on here in my parallel circuit, as all parallel circuits are. So, since you're following me there, so what do I need to do if I've got 9.43 amps and 5 amps? My power factor is going to be, right now, is going to be essentially 5 over 9.43, which is going to be something north of 50. It's like 51 or 52% power factor, right? Which is terrible. So here's what I want to do, is I want to create a triangle that looks less like this and looks more like this. And as my triangle gets flatter, as my reactive, my I at the reactive elements is a lot less than my I at the resistor, and they're both R's, I know, RES, resistor. As my reactive side becomes smaller compared to my resistive side, then this number here is going to, the hypotenuse is going to approach the same as this. As this guy gets smaller than this, what I like to shoot for is if I can shoot for this number 8 amps being kind of closer to only 20% or less of this number. Now the book has you do a whole bunch of math to get there, and you have to pull a bunch of numbers out and multiply by 0.96, and it's all good math and it makes sense and all. But for me, I just want to say to myself, I want that 8 amps to be a hell of a lot smaller. And I want it to be something in the neighborhood of 20% of what 5 is. Well, luckily, 5 is an easy number for me to figure 20% out. 1 is 20% of 5. So the triangle I'm looking for is going to look like this. It's going to have 1 amp, 5 amps, and some other current. So I'm going to have 1 amp reactive, I'm going to have 1 amp of current through the resistor, and then 5 amps of current through the resistor. And what am I going to have here? Well, I'm going to have 5 squared is 25, plus 1 squared is 1, so 26. Square root of 26 is 5.09 amps. And if I can do that, I haven't told you how to do that yet, but if I can get my triangle to do that, then my power factor becomes 5 amps, because it hasn't changed, over, instead of 9.43, over 5.09. And lo and behold, that comes out to about 98%, or 0.98 something something. So this is what I want to do. Now, how do I get there? How do I get to 1 amp? Well, check it out. Watch me throw the eraser on the floor. Check it out. All I've got to do is I've got to add another place for current to flow through another capacitor. That is in effect saying I'm going to add another capacitive branch to this circuit. And that's how I would do on any circuit, whether it was a parallel circuit like this, I'm just doing that because the math is easy for us to get our heads around, or if it was a series circuit, I'd add a capacitor in parallel to it. And that capacitor, I'm going to want to have, well, let's see, what would I need to do to this three-way triangle here to make this 1 amp instead of 8? Well, I've got 10 up here, so I need 9 over here. I've got 2, so I have to add 7 more amps. So whatever I do to this capacitor, I want it to be a 7 amp current flow around that capacitor to add to these 2 amps here so that I have 9 amps total. And that 9 amps compared to 10 will give me my desired 1 amp total when I do the subtraction. So how do I come up with that? Well, let's see. If I want 7 amps, let's go back to Ohm's law. If I need 7 amps and I know I've got 100 volts, what's my, in Ohm's law, R, but now we're dealing with X sub C. What's my X sub C going to be? Well, let's see. X sub C for R equals E over I, right? Back to Ohm's law. 100 amp, or 100 volts, is my E, and my I that I want, but don't have yet, is 7 amps. Well, 100 divided by 7, if I did my notes correctly here and can find them, is, I might just have to resort to my calculator. 100 divided by 7 is 14.28 ohms. 14.28 ohms. So that's how much X sub C I'm looking for, is 14.28 is going to be my X sub C. Well, how do I get to 14.28? Because I can't just go to the plat and say, hey, sell me a 14.28 ohm capacitor. They're going to look at you like you're crazy, right? Because they don't, it all depends on what the frequency is, depending on how you're using it. We don't sell capacitors by their X sub C. We've got to buy a capacitor, among other things, by its capacitance. If I would go to the capacitor store and say, hey, George, sell me a capacitor, he's going to have to know what, among other things, what capacitance is. So to solve for that, I'm going to go back to the formula I did up here before, and I'm going to say C equals 1 over 2 pi f X sub C. I have all those numbers. I can dump that into my calculator, and that's going to be 1 over 2 times pi times 60 times X sub C is 14.28. And if I dump that through, I'm going to get a number that is, and I'm going to erase this so you guys can see this number. The number my calculator gave me, and yours should also, is 0.0000185 0.0185755. Now, I want to reduce that to a usable number. I want to round that, but I want to round it correctly. Well, I don't have any millifarads, right? If I had some numbers in these first 3, those would be my millifarads. But I do have some microfarads. I have 18.5755 microfarads, but I don't really want to go that far out. I want to say I have 18.58 microfarads. You see how I did that? There's millis, here's micros. Those would be nanos, but I don't even want to go there. But I have 18.575, and I'm going to round that 5 up to 5.8, so that's going to be 18.58 microfarads. And I always accentuate my mu like that, so you can tell it's not an M, but 18.58 microfarads. And that's how I call up Platt and say, hey, George, sell me an 18.58 microfarad capacitor. And George is going to say, we don't sell 18.58s, and he's going to give you a range in the power that you need, you know, the voltage that you need of those. But you're going to be able to buy that. You're going to go ahead and figure out what the current is at 7 amps, so how am I going to protect that as an electrician? If I were to actually run this as a circuit, I would go ahead and put that on, if I was a commercial guy, I'd probably put it on a 20 amp circuit with 12 wire. If I was a resi guy, which I don't know why I do, maybe be doing power factor correction if I was a resi guy, but I would put it on 15 amp wire, number 14 gauge, and put it under a 15 amp breaker. Because I do need overcurrent protection on this. And that would be a circuit, and that would fix my whole system. Now, Whole systems, we're talking bigger numbers than this. But essentially, that's all we're doing. So the trick, and the thing I want you guys to remember is, first of all, when I get my triangle to this point, I want to say, hey, I want this number to be 20% or less than this one. I don't want it to be exactly that. I don't ever want to take my inductive circuit all the way into capacitive, which would be if I, instead of added 7, I added 8 and 8.5, 9 amps, something like that, of capacitance to this, because then my circuit would flip to being capacitive. And I want to just approach inductive. And I'm not going to go into all the reasons for that. Most people are looking for 94, 96, 98%. If you do 20%, if this guy is 20% of that, then you're going to have around 98%. If you go 15%, you're going to do even better, okay? So 1/5 is 20%, so 1 out of 5. Now, if this number wasn't 5, if this number was 100, then 100 amps here, then I could go somewhere under 20 amps here, because that'd be 20% of 100, and so on and so forth. Some numbers are easier than others to take that from. So that's essentially what I want you guys to be able to do. Try and keep it short today, so I'm going to end it there. I will give a nice practice sheet. Please look at the practice sheets after you've looked at this and see if you can follow what I'm doing on the practice sheet. And I love it when somebody calls me up or emails me and says, hey, you did something wrong in the practice sheet, because that tells me you guys are actually looking at it. You should also know that I can see in Moodle what you've looked at and what you haven't. I can see if you've watched the videos. I can see if when you downloaded the practice sheet, when you downloaded the quiz. Some of you guys who are running really late every time, I can open up your log and I can see, well, stuff was due on Thursday at 10 and they didn't look at it until Thursday at 6:30. So there's a reason I'm trying to put these videos out by Sunday and the quizzes by Monday. It's so that you guys have time to do it. If you get it right at the end of the day, I don't care. But if you don't get it right and there was something you could have done differently, then I kind of feel obliged to not give you as good a grade. So if it was up to me, everybody gets an A in this class. I really don't care about the grades, but I feel like just for integrity's sake, I need to say the guy that actually looked at stuff on Tuesday, Wednesday, Thursday, tried really hard, did it 99% right, he's going to get that 99% grade. The guy that didn't download it until Thursday evening and then didn't have enough time to do it right and made 3 or 4 stupid mistakes, he might only get a 70 or 80. Which is still passing. You're still getting the electrician. Honestly, there are a lot of good electricians that don't understand this stuff and can't do it. Is that me saying this isn't important? No, but if you want to be a really good electrician, if you want to move up into the ranks of the electricians that make really good money, this is stuff you want to know. So the next 2 weeks after this, we're going to have a little bit of, we're going to talk about transformers and we're going to talk about 3-phase. I don't even know which direction we're going to go, which one we're going to do first. I think I need to talk about single-phase transformers before I can talk about 3-phase at all. So we'll probably do single-phase transformers and an intro to 3-phase next week, and then the week after that we'll do 3-phase and 3-phase transformers. A couple things I'd like to cover are high-leg 3-phase panels. Talk about the issues with those, talk about the code requirements for that. Maybe revisit that multi-wire branch circuit thing that some of you did in DC, so the folks that were in my DC class from the get-go, we talked about that multi-wire branch circuit because that kind of rears its ugly head again. And surprisingly has a lot to do with that high leg. So a high leg is the 240 volt, 240, 120 delta, if any of you are familiar with it. And if you use B phase to neutral on that, you get the wrong voltage. You get too high a voltage and you blow stuff up. So ask your journeyman about high leg or wild leg or crazy leg 3-phase panels and 3-phase systems and see what they tell you. A lot of good information out there, also a lot of bad information out there. I will see you guys next week. Have a good one.